Simple rational graphs. Yes, that does mean that there are difficult rational graphs. My approach for this video is going to be looking at the parent function, which is y equals 1 over x, the most basic type of rational equation that you can build, just simply an x in the denominator underneath a 1. Okay, we're going to look at that graph, and then as we go through the video, what we're going to do is make transformations with that graph. Okay, so we're going to take a look at that graph, and as we go through the video, we're just going to be thinking about different basic transformations that we can do to this. All right, so let's start with the table of values. Let's choose all of these as x inputs. When we put that in for the x, what happens? Okay, what happens when we divide 1 by 1? You get 1. What happens when you divide 1 by 2? You get 1/2. Okay, and then if you divide by 4, you get 1/4. However, if you divide by 1/2, if you divide 1 by 1/2, you actually get 2. And we can show that with keep change flip. We could take 1, let's go ahead and write this as 1 over 1, divide that by 1/2. Keep change flip will multiply by 2 over 1, which gives you 2. Okay, in a way, what we're really getting for everything that we plug in here, we get back a reciprocal. That's what we get back. So if you're to plug in 1/4, you get back 4. If you plug in 0, that's different though, right? If you plug in 0, you're going to get an undefined situation. If you plug in -1, you get -1. If you plug in -2, you're going to get -1/2. But you can even think here that if you were to put -1/2 in, you would get back the reciprocal of that, which would be -2. It would maintain that negative, just give you a reciprocal. Okay, so let's plot some points here. We got a point at 1, 1, which is here. You got 2 and 1/2, which is here. You got 4 and 1/4 here. Okay, and of course you would have 3 and 1/3, but that one's a little bit hard to graph, so I skipped over it. Let's see, at 1/2, you get 2. Okay, so 1/2 goes up to 2. 1/4 gives you 4. And we start to get this shape. Let's fix that part right there. Okay, what's going to happen? As you move further out this direction, you're going to be taking reciprocals of your input, which are going to give you back smaller numbers closer to 0. We're actually creating an asymptote. Okay, we're getting an asymptote over here. The same thing happens here. Okay, we still have that situation reciprocals. So the smaller number you get, the bigger you're going to get back from it. This graph is going to approach the y-axis. You do have a vertical asymptote here. In fact, you've got asymptotes on both of the axes. Okay, now this isn't the only part of the graph, because remember we got negative numbers. At -1, you get -1. You get this point. At -2, you get -1/2. Back 2, down 1/2. You're here. Okay, likewise, if you went back 1/2, you would go down 2. Or back 1/4, down 4. You get the same picture, but in quadrant 3. And as mentioned before, we do actually have asymptotes here. You have a vertical asymptote at the y-axis. You have a horizontal asymptote at the x-axis. And this is the parent function for rational graphs. All right, just a couple of things here to address real fast. An asymptote is a line a graph approaches more and more closely while never making contact. Okay, the graph is going to get closer and closer to the y-axis, but it never actually makes contact. And over here, it's going to get closer and closer and closer to the x-axis, but never make contact. Okay, so those are your asymptotes. All right, one more thing. According to the table, but maybe even more so in the graph. If we think about this function, we'll realize that it is 1 to 1. It's going to be 1 to 1. Graphically, we can determine that this is 1 to 1 because it passes the vertical and horizontal line test. Okay, as we move a vertical line across it, the graph never makes contact with that vertical line more than once. Same thing horizontally. As we move along, the picture is basically the same image, just turned to the side there. So it doesn't make contact with it more than once either. Okay, this will be a 1-to-1 function. All right, another really neat thing about this one, though, is that if we were to draw a diagonal line, that would be y equals x. Okay, remember that inverse functions are reflections over that. You're going to notice that this graph itself is reflected around it. Okay, so if we attempted to look at an image of the inverse function by reflecting the graph over this line, you would get back the exact same picture, which means that the inverse to this is itself, which is a unique feature that this graph has. All right, so now what we're going to start doing is looking at basic transformations. What we're going to explore first is a factor that we usually refer to as an a-value. Okay, so remember the original parent function, which is just going to be 1 divided by x. Okay, if you were to multiply that by a number, the most appropriate place to put that number would be the numerator. Okay, just go ahead and multiply the 1 by that number. So for the first equation, we're using an a-value of 2. For the second, we're using an a-value of 0.25, which is the same thing as 1/4. Okay, so we have a number greater than 1. We also have a number that's less than 1. All right, so typically what the a-value does is it vertically stretches the graph. What's kind of interesting here is that the a-value, when it vertically stretches it, it does make it look like it's horizontally stretched as well. Okay, that's different from all the other functions that you've studied. All right, what I want to begin with is a graph of the parent function, just so that we have that as a basis. Okay, so some points that included would have been at 1, 1, at 2, 1/2. I don't have room for the next point I used, which was at 4 1/4. Okay, but I've got a point here. I can plot a point. Let's see, you got one here, you got one here. Okay, so rough sketch of the parent function. All right, so let's take a look at what happens with this. If you were to plug in a 1, if you plugged in a 1 there, you'd get back a 2. Okay, so if I go over to 1, the parent function gives you back 1, but it's going to vertically stretch it so that you end up over here at 2. Okay, now if you were to plug in a 2 into that spot, you're going to get a 1. Okay, so if I go over to 2, I get a point at 1, which the original function at 2 gives you 1/2. So everything is being stretched vertically by a factor of 2. That height has doubled. This height has doubled. And it's going to repeat that process. And we get this picture. The graph almost appears to also horizontally stretch. That space of 1/2 becomes a space of 1. This space of 1 becomes a space of 2. It is technically vertically stretching, but it does appear to be horizontally stretching as well. Okay, same thing over here. We're going to get a point here and here. All right, so let's see what happens with this guy. All right, now keep in mind that the numerator is the same thing as 1/4, is the same thing as 1/4. And my approach to graphing this one is to build off of what I observe here. Okay, if the 2 vertically stretches everything by a factor of 2, then the 0.25 is going to shrink everything to 1/4 of what it was. So if I were to go out to 1, instead of getting a height of 1, I get a height at 1/4. Okay? And if I go out to 2, instead of getting a height of 1/2, I get 1/8. And these points, I can basically just move them over here. Okay, so I got a point here, get a point here. So you're going to notice the graph gets pulled in towards those asymptotes. Same thing's going to happen here. All right, and just for the sake of demonstrating that these graphs are correct and to give you a slightly better image, I'm going to graph them in the calculator. Okay, so I went ahead and set up my window so that it looks just like the window that I have here. I've got these filled in. Go ahead and hit graph. That's the parent function. That's with the 2. That would be with the 1/4. All right, for example 3, I'm not going to really do anything too different than what you saw in example 2. What I want to do is highlight that when you have a value over x, such as 6, you can use the factors of that number to graph it somewhat quickly. Okay, now it's still going to have the same asymptotes as the parent function, which means it has an asymptote along the y-axis and the x-axis. All right, now I'm going to consider factors of 6. The factors of 6 in combinations would be a 1 and 6. We'd also have a 2 and 3. Okay, so if I were to plug a 1 in for x, I would have 6 divided by 1, which gives me 6. So I actually get a coordinate 1, 6. Or if I plug 6 in, I'd have 6 divided by 6, which is 1. So I get the flip-flop of that as well. I get 6, 1. The same thing is going to be true for 2 and 3. If I plug 2 in, I get 3. If I plug 3 in, I get back 2. So I get the coordinates 2, 3, and 3, 2. And real quickly, I have enough points that I can start to sketch the graph. And the graph is also going to exist in quadrant 3. And you would get that one by plugging in negative numbers. If I plugged in -1, I get back -6. If I plug in -6, I get back -1. Okay, they're going to be the same coordinates that you see here, in a sense, but in quadrant 3. Okay, so I can go back 3, down 2. I can go back 2, down 3. I can go back 6 and 1. Go back 1 and down 6. All right, for example number 4, we're going to go ahead and bring in the idea of translations. But instead of me providing the equation for you, I'm going to describe this in terms of function notation. Okay, we're going to let f of x be the parent function 1 divided by x. And again, instead of me writing the equation out, I'm going to describe the transformations in function notation, which is this over here. Okay, so inside of that, you're going to notice the x minus 2. That means that in our parent function here, the x is going to get replaced with x minus 2. Okay, so we've got 1 over x minus 2. All right, so the 3 that's out front is going to get multiplied by what we currently have, which is this part. So the best place to put the 3 will actually be in the top. Okay, so this will be 3 divided by x minus 2. The plus 1 is going to happen at the very end of it, which goes here. So this is our function. This is what we're going to be graphing. All right, now, how to actually graph that? This is going to represent a horizontal translation. This is going to represent a vertical translation. What I would suggest that you do here, because we're building off of the parent function, is to use those translations to move the asymptotes. Instead of having a vertical asymptote at the y-axis, this is going to have us move it to the right 2 units. So your vertical asymptote will be here, which should make sense because the value that you would plug in for x here to make the whole thing undefined, which creates the asymptote, is 2. And that's where we have our asymptote at. This is going to shift the horizontal asymptote up 1 unit. Okay, so instead of being at the x-axis, we're going to be here. All right, so for the most part, just go ahead and pretend that this would be the origin and that we had the function 3 over x, okay, because we already dealt with the minus 2 and the plus 1. Okay, so then from here, we should think about the factors that go into 3, which is really just 1 and 3. So those numbers will build combinations of coordinates that we could plot. From here, we can go over 1 and up 3, which doesn't actually fit on my graph. As well, you could go 3 units this way and up 1. Again, that doesn't fit. But I can still plot the points over here. I can go over 3 and down 1. I can go over 1 and down 3. Now beyond that, I'm not going to get any really nice coordinates. So I'm just going to use those two to start to sketch the graph. All right, so the graph is going to exist here. You're going to have that vertical asymptote, this horizontal asymptote. The graph will also exist over here. I just don't have room to draw it.
Wait, what?